Welcome to Aarush Coaching Classes, and here's the next
of heat energy required to raise the temperature of a body per unit mass. Correct? So I'll repeat it once again. The amount of heat energy required to raise the temperature of a body per unit mass. Okay. So basically, what is this? What are we talking about? Why am I learning and moving on with this? Because first of all, this will be used in your many things. Like, we'll be learning about different, what do you call is environments like isothermal, isobaric, isochoric, all those things. And for that, you need to know all these things. And that's the reason we are covering this. Okay. So I'll make it short, sweet, and quick. So this depends upon two things, Swapnil. First is the nature of the substance, whatever the nature of the substance. And secondly, it is based on the temperature. Correct? So the formula for specific heat is S equal to 1 by M del Q by del T. This is the formula. Okay. So what does of the body? What is del Q? You already know, heat energy, and T is your temperature. Correct?
Yep.
The unit is joules per kg per Kelvin, like this. So this is for joule, and these two are in denominator. So I've written kg minus 1 and Kelvin minus 1. Correct?
Wait, what is that the unit for?
Joules
Yeah.
per kg per Kelvin. So it is basically like joules and kg.
So that is the unit for specific heat capacity.
Yes, unit for specific heat capacity, S. Right?
Yeah.
Correct? Okay.
Yeah.
Now, moving on further from here, now we will talk about molar specific heat. Molar specific heat capacity.
Wait, what was the unit again? Joules per kg.
Joule per kg per Kelvin.
Per Kelvin. Okay, yeah.
Yeah. Okay. So now we will learn about molar specific heat capacity. So it is what? It is also the same, but instead of mass, we will be taking mole. And that is the reason we've written molar specific capacity. And what is 1 mole, Swapnil? From the chemistry you must be knowing.
1
Number
of
molecules upon
over molar mass, is it?
Molecular mass. Yes.
Okay.
Correct. Said it correctly. This is 1 mole. So can I write now like this? We write molar specific heat as C. Okay. So C equal to 1 by mu. We represent 1 mole by mu. And del Q by del T.
Wait, so can you say that again? C is specific heat capacity with
molar specific heat capacity. Molar.
So, okay. Molar. Can I just write this down real quick?
Yes.
Molar.
C is molar specific heat capacity. It is exactly the same as specific heat. Instead of mass, we will take mole. So if you have to write the definition, it will be exactly the same. Amount of heat energy required to raise the temperature of a body per unit mole. It was per unit mass. So that's the difference. Correct? Same definition. Okay. Obviously, the unit is also same. Joules per kg per Kelvin. Correct? Yes?
Yeah.
And it depends on what? See, that depended on two things: nature of the substance and temperature. This will also depend. First is nature of the substance. Second is temperature. And third, number 3, conditions under which heat is supplied. Why? Because it is mole. You remember when more heat, the gaseous and the molecules start running faster and all those things, right? So here the third thing will come, that conditions under which the heat is supplied. So it will depend upon how many things? 3 things. So 1 mark questions like molar specific heat depends upon, or specific heat capacity depends upon. So you have to give the right answers. Or they will have 3-4 options. You have to tick mark like that. Okay? Now, when I talk about this, so have you written this, Swapna?
Yeah.
Yeah. Okay. So when I said ki it depends upon the condition under which the heat is supplied, so this molar specific heat is of 2 types, Cp and Cv. So what is Cp? Molar specific heat capacity at constant pressure. So molar specific heat capacity at constant pressure. And this will be molar specific heat capacity at constant
Velocity or volume.
Cv. And for ideal gases, what happens? Cp minus Cv is equal to R. That means this minus this will give you R. And what is R? Universal gas constant.
What is Cp and Cv? Oh wait, it just
Molar,
says yeah.
Molar specific heat capacity at constant pressure and at constant volume. Okay. So why are we doing this, Swapnil? Because we have a derivation, very important derivation, which either comes in exam. If it will not come in exam, but it is important. Sometimes they actually ask you to do this derivation. And that's what I will explain you when you said ki what exactly is Cp. Okay, so we will look into it. All right. So this you have to remember. Cp minus Cv is equal to R. R is the universal gas constant. Yes. So R has some value also, which you will take it out and tell me. Okay. Later on. Maybe from your physics or chemistry book, wherever you get the value. Okay?
Yeah.
All right.
Yeah.
So what we did, we started off with specific heat. Specific heat is 1 by m del q by del t. It depends upon two things, the nature of the substance and temperature.
Wait,
Okay.
you know how it says 1 over m and del q over del t? Is that times or is that like what does
Temperature.
what?
Temperature.
No, I don't mean that. I mean because there's two different fractions. Like,
Yeah.
so what's happening between the 1 over m and the del q over del t? Are they timesing or are they just by themselves? I'm confused.
Okay. I will tell it again. Wait. See, S is written like this: 1 by m del q by del t. Correct? So this will be multiplied. This will be del q. You can write m del t. That's all.
Okay. So they are multiplying. I was just making sure.
Yeah. Same way for the molar specific heat, it will be 1 by mu. The rest all remains the same. So this will be like del q mu del t. That's all. This is just a multiplication, right?
Yeah.
Correct?
Yeah.
Okay. So I'll revise it once again for you. Specific heat is this, and it depends upon two things: nature of the gases and the temperature. Then we learnt about molar specific heat, where mu represents 1 mole. And what is 1 mole? Number of molecules upon molecular mass. And this depends upon three things: nature of the substance, temperature, and the conditions under which under which the heat is supplied. So what are those conditions? Those conditions are constant pressure and constant volume. And since we have C representation, we represent constant pressure as Cp and constant volume as Cv. Correct? For ideal gases, when you subtract these two, you get R, and R is known as the universal gas constant. It has some value, which is like a question or maybe a homework for you, which you will do and confirm. Okay. Now, the theoretical question which comes, or generally which is asked is, the question is, you have to prove Cp minus Cv equal to R by first law of thermodynamics. So I said to you, Swapnev, that Cp minus Cv is equal to R. So you said, ma'am, I don't believe you. Please prove me. Tell me, how is it? How it came? So now we will see how this proof comes. All right? Ready for it? Chale. So Swapnev, the first thing, tell me, what is the first law of thermodynamics?
Is it just the Q equals to U plus W or something?
Correct. So this is your first law of thermodynamics. Correct?
Yeah.
Okay. Can I write work done something else? Can I write it like this?
Yeah.
What is work done? What is work done? Seem to be?
I am not sure.
Not sure. Work done. Work done is represented in two forms. One is in the force form, one is in this form. Come on, Swapnev. We need to brush up. Tell me.
Distance.
Give me the formula with the force and give me the formula in the form of pressure. Both ways. Think. I'll give you 2 minutes.
Force and distance and pressure and volume.
Yes. How? So one way of writing force is what?
F.
Work done is force into distance.
Distance.
Correct? Force exerted and the distance it moved, or the displacement actually. Correct? Okay. Any other formula for this other than F and D?
Pressure and volume.
Correct. So where did we get this pressure and volume from?
I'm not sure.
When we learnt about energy, dear. Correct? Yes or no?
Yeah.
So in the energy, we learnt about work done is equal to power into T, the second formula. Correct? What is power?
Power.
Work done and T is the time taken. Correct? Power into time taken. Correct?
Yeah.
Yes. And then what is the third formula? P into V.
It is.
Check. Confirm.
Pressure and volume.
Yes. See, it is generally in the cases of gases. Okay. So, work done by gases is sometimes called the pressure volume or PV work done. And how do we do it? We check the pressure applied against a constant, this thing. So there will be work done. So see, if I have to explain you something like this, there's a beaker, and there are gases in it, and there's a what do you say? Your Coke bottles are there, correct? Yes. So what happens? You take out and you see the fizz, the soda, the water. It comes with a high this thing. Why? Because there was some pressure and you applied, it came out. Correct? In the Coke bottles or the Pepsi bottles, correct?
Yeah.
Yes.
Yeah.
So that's what. See, at the top they have that. The what do you call that? The cap of the bottle or whatever. When you unlock it or bottle it, you see the fizz coming it out. Correct? Why? Because we hold it through a pressure, and as soon as you remove it, it moves away. So that's where the work done is. So there is some work done, right? Even in Sprite's bottle, if you see, there's some Sprite, and you have it like this. Correct? This is the one. As the more you dip into it, the more you keep on pressing this. What happens? The gases are coming up. So that's we are doing work. We are applying pressure on this. So there's some work done. This is moving. Okay. So that is the third type of work done.
Yeah.
Correct. So this we talk about in the terms of work done. So work done is represented in 3 different formulas. You can check also. Maybe you must have studied in the starting chapters. If not, so you have come to know this way. So this is one. Work done is force into displacement. Second is power into time. Third is pressure and volume, PV. Correct? Okay. So now I will rub this and we will take it again back to our proof. Correct? So what I did, I wrote work as P into V. That's what I did. Work is P del V. That is what I have written here.
Mhm.
Correct?
Yeah.
Now, what am I saying is at constant volume, what will happen?
At constant volume.
Constant volume means volume will become zero.
Mhm.
When I'm saying at constant volume, the volume will become zero, correct?
Mhm. Okay.
Why zero? Because we said change in volume and I'm saying it is constant, so there is no change. So that's why volume becomes zero, correct?
Mhm. Yeah.
So that is why this formula,
Why is it change in volume?
it is always change. We are always representing change. The starting work done, the less work done. We are always representing this.
So it's always change in volume.
Yes, change in internal energy, change in
Then what about the other formulas? Like, what about displacement?
displacement. Okay, displacement is F dot D. Then there's an angle. If the force is applying and it is getting displaced, then there's an angle one. Then we apply FD cos theta. You remember?
No.
Oh, the starting chapters of physics. No, Swapna? Angle
No, I
and
don't
all
remember that.
you haven't
Uh,
studied.
we've done.
Okay. Okay. So
I
I need
think we
to.
maybe have. I don't
Yeah,
know
we
if it's the
will
same
do.
thing. We've done something similar, but I don't know if it's the same thing.
Okay, so what is, I think I have not covered. I have just started with thermodynamics, but I think I need
Mhm.
to revise these chapters also with you. All right. So, Swapnil,
Mhm.
what we'll do is I will revise those chapters also with you. Let me
Yeah.
finish this one. And then
Yeah.
maybe after thermodynamics, first we'll have a revision session of all the chapters till now.
Yeah, that
And
would
then
be
I
good.
will take it forward. Correct?
Yeah.
Otherwise, I think you will get confused a lot. Okay. So,
I'm
Swapnil,
already
what
confused.
happens? Yeah. See, even if you don't want to take, suppose you don't, you say, ki, no, ma'am, I don't want to take del V. I mean, change in V. Okay, don't
Mm-hmm.
take. I'm saying constant volume. Volume is not changing. It is
Mm-hmm.
zero. So
Yeah.
then in that case, this formula becomes what?
0.
Del Q equal to del U. This is equation number 1.
Wait, I'm confused. Okay. So why is that's equation 1. I thought that was a -1. Okay. Yeah, that makes sense. Okay.
Okay. Why?
Yeah.
Because I said del V is equal to 0. So when you put del V 0 here, so this thing will become 0. This thing will become 0. So you are left with del Q equal to del U. That's it. That's what I have written here. Correct?
Mm-hmm. Yeah.
Because I said del V is 0. If you put this 0 over here, P into 0 is 0. So del U
Mm-hmm. Yeah.
plus 0 is del U. So del
Yeah.
Q equal to del U. That's what I have written. Del Q equal to del U, equation number 1. Correct?
Yeah.
Yes or no? Hmm.
Wait, so when I searched up the first law of thermodynamics before,
Hmm.
it had del U is equal to Q plus W, which is
Correct.
like a little bit different to this one. But like, why is it still plus? And then like, why is it not like change and all
See,
of
it
that?
is same only. It is same only.
Yeah, and it's the same things, but like if you rearrange it, then like it would be
Yes.
minuses, right? So like, why
That
is
is
it
what
like
our question is. You have to prove Cp minus Cv equal to R by first law of thermodynamics. So first we have quoted our first law. This is our first law. Now what
yeah,
we did
but
is
when
we
I
changed this.
okay, yeah.
Huh. You were saying something.
Okay, no, I was just saying, yeah, that's like the first law that like you taught me, but when I search it up, it's like a little rearranged, but it's still positive. I was just asking why is it still positive? Like, why is it? It's U plus. I mean, U equals to Q. Change in U equals to Q plus W.
Change in Q plus W. Okay, see, what happens is, Swapnil, why do we write change? That's what your question is, right? You are saying that why can't I write it like this, correct? U
No,
plus
no, no.
W.
It's the change isn't really the question. It's more of like, why is it positive? Because so there's a change. It's change in U. Change in U is equal to Q plus W. So like, because it's like how we rearrange to find the internal energies. It's like before when I changed it to find the internal energies, right?
Yes.
Then it was like negative, but this time it's all positive. I'm just confused about that. I'll try and send like a picture so it's easier to explain.
Okay, you want to share your screen, is it?
Let me see if I can just send a picture of what I'm saying. Otherwise, I will share my screen.
Okay. So you're sending now?
Yeah.
Okay.
It's just this because it's slightly different to how you wrote it. Can you see the whole picture?
Yes. Yes. So it is one and the same thing, right?
Yeah, it's the same. It's the same units, like
Yes.
as QWU, but we moved U to the other side,
Yeah.
and we moved them around, but it's still all positive. I was just wondering how it's all positive. Because usually when you move something to the other side, wouldn't it be negative?
Okay. So Swapnev, see, you also know minus and plus will depend upon the conditions. Correct?
Okay.
I told you when it is by the system and when it is on the system. So that is why they have just written a generic formula. And what they did is they just rearranged it because they want to keep the change. They are trying to tell you, see, what they have done in this formula is, they have written it like this, correct? Q plus W, correct? So what they are trying to tell you is this, only this is changing. These two are not changing. So that's what they are saying, like del U is basically U2 minus U1 is equal to Q plus W. But you also know very well that this Q and W will depend minus or plus. Okay, so it's just the way of writing it. There's nothing
Okay, so the
wrong.
minus and plus it doesn't matter.
Yes, yes, yes.
Okay.
Any way you can write it. Mostly it is written either this way or in the positive form only.
Yeah.
See, your question will be like, why if it is written like this, it should be, this should come here and this should come, so minus should come. So even if you do that way, minus gets cancelled.
Yeah.
Correct? So it is just the way of writing. That's all. Okay.
Yeah.
And don't worry with the minus and plus sign because you also know it is on the system and by the system. Accordingly, it will.
I need to look at that again. But also what you were saying before about the changes. Why don't they have changes in them? Is that they just wrote it like that to show that they aren't changing?
Yes, because when you when you study for the first time, you learn A, B, C, D. Okay. But when you learn after a year, you learn, okay, capital A is also represented as small a. And then maybe in the after ages, you learn, okay, it can form sentences, right? So when you introduce first law of thermodynamics, generally people write it like this. It's just general notation. Okay. But obviously it represents a change because there are some changes happening. Correct?
Yeah.
So mostly, I mean, if you talk in the technical terms or this way, you should write change form. But yes, in some books, it is written this way. It is just the notation style of writing. So you can write it this way also. Not a problem. Correct?
Okay, so you don't have to write the changes.
Yes, yes. When you are writing first law of thermodynamics. Here we are writing changes because we are trying to prove some point. Correct?
Yeah.
We will say volume 2 and volume 1. And on that note, what I will do is I will quickly explain you that PV wala thing also, so that you don't get confused. Okay. So see, suppose I said work done is what? Force into D. D is what? Distance you can say, or displacement, whatever you want to say. Correct?
Yeah.
Okay. So now force, can I write it like P into A?
Force is
pressure into area.
area.
Can I write F as pressure into area? Can I write it like this?
I haven't heard of that, but probably.
So many things. Okay. So I'm just telling why I came to PV. And then when you write it like this, area into this displacement is volume. So P into V. And that's how work done equal to PV comes. I mean the derivation of this I told you.
Okay, wait, let me just see this again. So work done equals the force times displacement.
Correct.
Which is
and
equal
force is written as pressure into area.
Area, yeah.
And then we combined area and displacement together, which is called volume.
Okay.
So why area? Area is Swapniv like this. Correct? Length and breadth. And this is getting displaced. It's going to a height. So length into breadth into height makes what? Volume.
Volume, yeah.
Correct. So what did you understood? See, this is an area which is getting displaced. That means it is going to a height. So that means length into breadth into height, which is a volume. So that's what we have written. Correct?
Yeah.
Yes. And if you talk about this, see, if here are gases, and this is called a piston generally. Okay. So what do we do is when you apply pressure, you are applying pressure here. Okay. So there it goes inside. So pressure is applied, it is getting displaced, and there's a work done. Maybe gases will go up or maybe gases will go down. So that's what the overall thing is happening. Like, why do we write P into V? Correct?
Yeah.
So this is all about all the work done and all the basic concepts. Okay?
Yeah.
All right. So shall we come to the point where we were doing this? So equation 1 is clear to you?
Yeah.
Yes?
Yeah.
Okay. So when we have done this equation, what we will do is now we will write this equation in the form of U. I mean, we will represent this U in some form. And what is that form? We will write it like this. See, I wrote it like this. Del Q is equal to del U. That was my equation 1. Correct? Now, I said it is at constant volume. So, constant volume means CV. Can I write it CV like this? Del Q by del T at constant volume. Can I write it like this?
Yeah.
Okay. Now, since in equation number 1, del Q is equal to del U, can I also write it like this? This is del. Okay, change. Can I also write it like this?
Yeah.
Yes. So basically, I can write del U by del T. What? At CV, at constant volume. Correct?
Yeah.
Now we will talk about at constant pressure. CP. Okay. So at constant pressure, what will happen? Del Q by del T. This is pressure. This will now become what? This will now become this plus P del V. Why? Why P del V?
Because Q is equal to U plus W, and W is U equal to pressure
PW.
times volume.
Yes. Yes, exactly. And now what will I do? I will divide these two. Del U by del T at constant pressure plus P del V by del T at constant pressure. Can I write this equation this way?
Yeah.
Okay. So basically, what will happen? Okay, have you noted down?
I noted down the first part. I need to write this part down.
Okay, so should I go back on the slide or should I move front?
I just need to write this part down.
Okay, please write it so that I can quickly tell you.
Okay, I'm done.
Done? Okay. So Swapnil, what will I do? See, CV is this, correct? CV is this. CP is this, correct?
Yeah.
Yes. Now what we have to prove? We have to prove CP minus CV, correct? CP minus CV. So what is CP? Let's check from here. We will write it from here. CP is
U over T.
del U by del T.
Del T.
Correct?
Mm-hmm.
Plus P del V by del T. Correct? This is what is CP minus, which is minus, this minus I'm talking about.
Yeah,
minus,
that is CP, yeah.
Minus CV. So where is V? CV is this. CV is this. Correct? Del U by del T. So
Yeah,
can
del
I
U by
write
del
it
T.
like this? I will make it like this for you. Del U by del T.
Yeah.
Correct? So
Yeah.
basically,
So you just cross them out.
Yes, this is CP and this is CV, and this minus is from the formula we've taken. Correct? Okay. So when I open this bracket, what will happen? Del V by del T minus del U by del T. So minus and plus gets cancelled. And you are left with what? P del V by del T. Correct?
Yeah.
Correct or no?
Yeah.
So this is what? This is your R. Now you will say, okay, ma'am, how did you say it is R? Okay, so I will tell you. By ideal gas formula, what I told you, PV is equal to RT. Correct?
Yeah.
So here, what will I do? I will write it P del V. Why del V? Because we are taking change. Mu will be 1. Why we are taking 1? Because we want molecular, the molecules are 1. Ideal gas is mu, we will take 1.
Instead of U, can I write N?
Yes, you can. Okay. Del T, and then R is what? P del V by del T, which is equal to R. If you take this down, it is exactly the same, which is equal to R. That means hence root.
Oh, okay. So nRT. So what did you do?
Okay, I will do it once again for you.
Okay.
Okay. See, Cp minus Cv. So what is Cp? Let's see what is, this is Cp, correct?
Oh no,
So
I
now
got
I'm,
that part. I got the CP minus CV part. I meant the PV-nRT part.
okay, I will do it for you, no problem. So what will I write? I will write it like this: del U by del T plus P del V by del T minus del U by del T. This and this gets cancelled. So we are left with P del V by del T. And which I am saying is R.
Yeah.
This is Cp minus Cv, Cp minus Cv, and I will say hence proved. But you will say, where did the R came from? So we will write, for ideal gas, what will happen? PV is equal to
nRT.
nRT, and we are taking as 1. And we are taking as 1. So
Wait,
1
why do
multiplied
we take it as 1?
because it is ideal gas.
Oh, okay. So ideal gas N will be 1.
Yes. Okay. And when I take this, can I write it same thing in the del form, R del T? Can I write it like the same thing? Change. Volume is what? Change in volume.
Yeah.
T is what?
Yeah.
Change in T. And then I'll bring this T down. That is P del V by del T is equal to R. So this is what I did.
You can just add like the changes like when you need them, right?
Yes.
Yeah, you just add the. Okay. Yeah. Okay, I get it.
Yes. So that's how the proofs are done. That's how the proofs are made. Okay.
Mm-hmm.
Okay. So you can write this. I want to tell you 2 more things. Just remember those things, and then we will take it forward from there in the next class.
Mm-hmm.
So Swapnil, this will help you in your chemistry formulas also. This, like today's class, what we've learned, no? Molecular mass, this and all. This will also help you in your chemistry. I don't remember which chapter it is, but somewhere where you learn about gaseous state and all, that time it will help you.
Yeah.
Okay. All right. So have you noted down this?
Yeah.
Okay. So Swapnil, quickly I'll tell you 2 more things. Specific heat ratio, that is called Y. Specific heat ratio, that is Y. It is not important for your physics, but it is important for your chemistry, specifically for numericals. Okay, so since we are discussing, I'll tell you right away here. So Y, I mean the specific heat ratio is defined like this, Cp by Cv. Okay, and it is different for different gases. So when I talk about monoatomic, okay, so you will learn about all these gases in your chemistry. Monoatomic gases, when I talk about, it is Cv is 3 by 2R and Cp is 5 by 2R. Please remember them. And when you take Y, like Cp by Cv, that is 5 by 2, 3 by 2, 2 gets cancelled, 5 by 3, which will give you 1.67. Please remember these. There's a table in chemistry which they give you at monoatomic gases. What is Cp, what is Cv, what is specific heat ratio? You should know. Cp is this, Cv is this, and Y is this.
So Cp is 5 over 2 R and Cv is 3 over 2R.
And Y the specific
Y is Cp
ratio
over
is
Cv.
1.67.
Okay.
For monoatomic gas.
1.67.
Okay.
Yeah.
Same thing. Have you noted down?
Monatomic gases.
Yes. Same thing for diatomic.
5 over 2 and Cv equals to 3 over 2.
Diatomic, where we have 2. So again, same thing. Cv here is 5 by 2R Cp here is 7 by 2 R, and when you take out specific heat ratio, it will be Cp by Cv, which is like 7 by 2, 5 by 2, RR cancel, 2 cancel, which is like 7 by 5, and you will get 1.4.
Wait, so you just have to remember these, like,
Yes.
there's no way of working them out?
Yeah, because there's a big table. You check in your chemistry, you will have for
Mhm.
all the gases, triatomic and so on. So first two I
Yeah.
have told you, which generally comes in numerical. Whenever you will do chemistry numerical, no, that time you will face this values
Yeah.
of Y and
What is the most common they give you? Are these the most common, like
Yes.
monatomic and diatomic?
diatomic. Yes, these are the two most commonly used. Rest all, there's a big table. You can go through it. Many are there, but you don't have to remember all. Only monoatomic and diatomic. So you can say for monoatomic 3 by 2, 5 by 2, and just double for diatomic 5 by 2, 7 by 2. So that way you can, so even you can remember one and then do it.
Yeah.
Correct?
Mm-hmm.
So we will stop here, Swapnil, and we will start with the processes we have to do, the isothermal, this thing, and then we have our heat engine and all. So we need at least 2-3 classes more for this.
Yeah.
Heat engine and many things are there in this.
Mm-hmm.
Okay. All right. So
Yeah.
thank you so much, Swapnil.
Yeah. Thank you.
Okay. Bye.
Thank you so much. Please like, subscribe, and share.